So today I would like to talk to you about the Frisch-Waugh-Lovell theorem, which is a famous theorem in econometrics, but basically is based on linear algebra. So consider a setting where you have a data set containing a vector y and a matrix x, and here y is just a vector, an n times 1 vector of observations, y1 until yn. Okay, so this is simply an element of Rn. And our x is the matrix of covariates, and we have k covariates, so it's an n times k matrix. So we can write it in terms of its columns. So we have column x1 until xk, and then of course every column xj also has n observations, xj1 until xjn. Okay, so this is what we have. We have a vector of dimension n, and then we have a set of k covariates. And what we would like to do is we would like to regress the vector y on the covariates in x. So we want to regress y on x. So what does this mean to regress y on x? Well, it basically means that we're going to take a linear combination of the columns in x. So we're going to multiply x by a vector b. So x is n times k, and b is going to be k times 1. So it's going to be a vector of size k. So it's going to take linear combinations of the columns in x. And we're going to do this in order to make x times b as close as possible to y as possible. Okay, so we're going to choose b such that x times b is close to y. Close to y, basically we're going to say that the distance between this vector here is of size n times 1, and this vector here of size n times 1 is going to be as small as possible. So basically what we would like to do is we would like to minimize the distance between xb and y. You can do this using the norm by choosing b. Okay, so this is a problem in linear algebra. So what we can do is we can look at the space Lx. This is a space of all linear combinations of the columns of x, where b ranges over Rk, and you see that this is a linear subspace. In a sense, all linear combinations of vectors here is also going to be in this set. Okay, so this is linear subspace, and what we want to do is we want to find the element in this linear subspace. We want to find xb that is as close as possible to this vector y. So basically the problem is the same as finding a y hat in this linear subspace such that the distance between y hat and y is as small as possible. And we know how to do this. Well, if we have a linear subspace, example here is the vector 0, you have the linear subspace Lx, you have the vector y, which might not be in this linear subspace. Finding the element in the linear subspace that's as close as possible to y, for example, is going to be here the y hat. We know that the properties that this y hat will satisfy is that this vector, y minus y hat, is going to be perpendicular to every vector in this linear subspace. Okay, so basically the angle that this vector makes with every vector in the linear subspace will be equal to 90 degrees. So for every z in this linear subspace, what do we have? We have that z prime times y hat minus y going to be equal to 0. Y hat, well, what's y hat? It's an element in the subspace, so we can write it as x times b, maybe b hat, minus y times z prime is going to be equal to 0. And how are we going to find b hat? Well, we're going to take particular elements of z. So what we can do is here we can pick the b's that are 0 everywhere except equal to 1 at some position, say j, then of course x times b will be equal to the jth column of this matrix x. So every column of x will be orthogonal to xb hat minus y. Okay. And if you take the transpose of x1 over the transpose of x2 and so on, you can do this for all k columns of x. You get the transpose of the matrix x, so we stack all these equalities on top of each other, and what we get is that x prime xb hat minus y should be equal to 0. X prime x times b hat is equal to x prime y. This is all equivalent. And if this is of rank k, then we can invert this. So we have that b hat is equal to x prime x minus 1 x prime y. Okay, and this is the well-known OLS, ordinary least squares estimator of the regression of y on x. Okay, so maybe this is already familiar to you, but what do we do now with this OLS estimator? Well, let me just recap here. We have this beta hat is equal to x prime x inverse x prime y. What we can look at the element xb hat, right? So this was equal to our y hat. This was the approximation of y in this linear subspace. Well, we just plug in b hat here, so we get x times x prime x inverse x prime y. Okay, and you can check that x is of dimension n times k. This is of dimension k times k because it's the inverse of a k by k matrix. This is of dimension k times n, so this matrix here is of size n times n, and you multiply it by a matrix of size n times 1. So we get something times n times 1. This matrix here, n times n matrix, is a special one, and we give it the name Px. It's the projection matrix onto the linear subspace Lx. Okay, and there's some nice things about this matrix Px, because if you take the transpose, what do you get? Well, you take the transpose of x prime x inverse x prime, which is equal to the transpose of this one, which is x times the transpose of this matrix x prime x inverse, but x prime x is a symmetric matrix. Inverse of the symmetric matrix is symmetric, so this is simply the same as x prime x inverse, and then times the transpose of this here x. So we get that the transpose of Px is equal to Px, right? So the matrix Px is a symmetric matrix. The second thing to notice is that if I take Px and multiply it by itself, this is simply x prime x inverse x prime times x prime x inverse x prime, and here the middle part, x prime x and x prime x inverse. Well, if you multiply these two together, they're each other's inverse, so this would simply give you the identity matrix I, n by n identity matrix. Okay, so this basically drops out, and we are left with x prime x inverse x prime, which is the same as Px. So Px times Px here is equal to Px. This means that Px, this matrix Px, is idempotent. Okay, so these are two interesting properties to remember. Another matrix that's important is the residual matrix. So if I take y and subtract the estimate of y, the projection of y into the linear subspace, well, my y is y. My y hat is equal to Px times y. Okay, so this is what's written here. And I can, of course, simplify. This is equal to the identity minus Px times y, and I call this matrix the identity minus Px equal to mx. Okay, and a good thing to know is that if I take the transpose of this matrix, this is I minus Px transpose, which is equal to the identity transpose minus px transpose. The identity matrix is symmetric. Px is also symmetric, as you have seen, so this is the same as Lx, right? So also Mx is symmetric, and if you multiply Mx by itself, get I times Px times identity minus Px. We multiply out this product, we get the identity times the identity is the identity, minus Px plus Px times Px. Px times Px, Px is idempotent, this is Px, so we have identity minus 2 times Px plus 1 Px, which gives you I minus Px equal to Mx. So also Mx is a matrix which is idempotent. So to recall, projection matrix, residual matrix are both symmetric and idempotent. So now let's go to the Frisch-Waugh-Lovell theorem, finally. So consider a setting where you have this data set yx, and now we split up x into two parts, right? So x is x1 until xk, and we somehow divide this into two parts, and we call the first part xa, for example, and the second part xb. Okay, so x times b, right, this matrix product, you can now write x as the composed of xa and xb, and then you multiply by b, so b also will have two components, the components for xa, which we call ba, and the components for xb, which we call bb. Okay, and of course if you regress y on x, what do you get? You will get a b hat. Okay, and this b hat will be composed of two components, one ba and one bb, so we can call this b hat a and b hat b. Okay, so this is simply regressing y on x. You get the OLS estimate b, which is given here, and you can split it into two components, the ones for the columns of xa and the ones for the columns of xb. Okay, so this is first regression that you do. Then in the second regression, what you can also do, you can regress y only on xb. Okay, should be capital B. What you get from this is you can get OLS estimates, and then you get the estimated call this maybe y hat b, pxb y, alright, this is the projection, and then you get the residual, let's call this y tilde as mxb times y. Okay, once you regress y on something, you get the projection here, the projection, and then you get the residual. Third instance, what you can also do is you can regress all the columns of xa on xb. And here also you get an x hat a, which is a projection matrix obtained by xb times xa, and you can get the residual x tilde a, which is the residual matrix mxb times xa. Okay, so what you have done here is you have regressed y on xb, you get the residuals, you regressed xa on xb, you get the residuals, and then in the third instance, there's three steps to the Frisch-Waugh-Lovell theorem. You regress yb, the residuals here of regressing y on xb, on x tilde a, the residuals of after regressing xa on xb. And of course this will give you OLS estimates. Let's call them beta hat a. Okay. Now what does the Frisch-Waugh-Lovell theorem tells you it tells you that this b hat a and this estimate beta hat a are identical. Okay, so this is the Frisch-Waugh-Lovell theorem. It says that if you regress y on xa and xb, then the coefficients for a are the same as if you would regress the residuals of the regression of y on xb onto the residuals that you obtain after regressing xa on xb. So what you can do is you can regress y on part of the covariates. You can regress the first part of the covariates on the second part of the covariates. Take the residuals from both regressions and regress one on the other one. The coefficient that you will get will be the same as the coefficient of the original regression. So this is the Frisch-Waugh-Lovell theorem. The goal, of course, is now to prove it. Okay. So the proof is not that difficult. It's a bit of linear algebra. So remember the orthogonality conditions. So if I regress y on x, the orthogonality conditions told me that x prime times xb minus y should be equal to 0. Okay. Now x is composed of two parts, xa and xb. Okay, so x prime, basically what this is, it's the matrix x prime a on top of x prime b, and then x times b, well, is equal to xa times ba, should be a hat, right, plus xb times bb minus y is equal to 0. Okay, so here these are the first rows corresponding to the covariates of A, and these are the second rows, second part of the rows corresponding to the covariates in xb. So we can split this up into two parts. We have that x prime A times xa b hat A plus xb b hat b minus y is equal to 0, and then the second part we have that x prime b xa b hat a plus y xb, sorry, b hat b minus a is also equal to 0. Right, so we have two sets of equations, one for the columns in xa and one for the covariates in xa, sorry, and one for the covariates in xb. So what are we gonna do? We're gonna rewrite this in terms of b hat b, and then we're going to substitute the expression that we get here into the first equation and see what we will get for b hat a. Okay, so if you rewrite this here, get xb times xa b hat a plus x prime b times xb b hat b minus x prime b y is equal to 0. Solve this for b hat b, is b hat b times x prime b xb is equal to x prime b y minus x prime b xa b hat a. Gonna pre-multiply both sides by x prime b xb inverse. Here we get b hat b is equal to x prime b xb inverse x prime b y minus x prime b xb inverse x prime b xa b hat a. Okay, oh, very nice. And now we're going to substitute this into the first equation. So the first equation can be rewritten as x prime a xa b hat a is equal to x prime a y minus x prime a xb b hat b. Okay, and here we have the b hat b, and we're going to substitute this by this. So we're going to have a long derivation here, minus x prime a xb, and then here this first term, which is x prime b xb inverse x prime b y and then the second part is x prime a xb times this with minus sign, so this becomes a plus, x prime b xb inverse x prime b x a b hat a. Okay, so one thing to notice is that this here, xb x prime b xb inverse x prime b, this is nothing else than the projection matrix pxb. And here we have the same thing, right? This is the projection matrix pxb. So this simplifies a little bit the notation. So I have x prime a x a b hat a is equal to x prime a y minus x prime a b x b y plus x prime a b x b x a b hat a. Okay, I'm almost there. Here I have x prime a no. Here I have x prime a, and here I have x prime a, and here I have x a b hat a, and here I have x a b hat a. Okay, so what I'm going to do is I'm going to plug in here the identity matrix, right? Here in between, and then what I have is x prime a, the identity minus pxb, and then x a b hat a. Okay, and here on the right hand side, here I have x prime a, here I have x prime a, here I have y, here I have y, so I can plug in here the identity matrix, and I get gathering terms is x prime a I minus pxb times y. And here I time minus pxb, that's just the residual matrix xb, and here I have the same, the residual matrix xb. So I get x prime a mxb x a b hat a is equal to x prime a mxb y. I left a little bit of room because mxb is idempotent, so it's equal to mxb times mxb. Okay, so I can just multiply this by mxb without changing anything, and then I can take the transpose of both of these also without changing anything. So in the end what I have is that I have mxb xa times mxb xa b hat a is equal to mxb xa prime times mxby. And here this is simply the residual that I get after regressing xa on xb, which I called x tilde a prime. This is x tilde a, b hat a is equal to here x tilde a, and here I have my y tilde. Okay, the residual that I get after regressing y on xb. Alright, so in the end I get b hat a. If I invert by the inverse of x prime, x tilde a prime x tilde a, get x tilde a prime x tilde a inverse x tilde a y hat. And this here, you recall this is my beta hat a. This is the coefficient that I get after regressing y tilde on x a tilde. So this is basically the Frisch-Waugh-Lovell theorem that says that this here b hat a is equal to the beta hat a that you get after regressing y tilde each every time as y tilde b, okay, on x tilde a. Right. There's a small note to make that I would like to make. So we had that b had a coefficient for the covariance on a on the regression from y on xa and xb is equal to x tilde a prime x tilde a inverse x tilde a prime y tilde. Okay, and x tilde a prime was nothing more than mxb xa tilde mxb y tilde was mxb y. I can write this as xa mxb tilde mxb y. These here, mxb times mxb is mxb, and I can take it back here, so I can also write this as mxb xa prime times y, which is equal to my x tilde a times y. Okay, so I've just rewritten this. I've written it out in terms of the matrices M. I cancelled one of them and I brought it back into the x tilde a. So this shows that b hat a is also equal to x tilde a prime x tilde a inverse x tilde a prime times y. Right, so here we lose the y tilde. From y tilde we go to y. And this here is the OLS coefficient from regressing y on x tilde a. Right, so we see that b hat a is not only the same as the OLS coefficient when I regress y tilde on x tilde a, but it's also equal to the OLS coefficient when regressing y on x tilde a. Right, so we don't need to take the residual for y. Okay, so what the Frisch-Waugh-Lovell theorem tells me is that if I take b hat a from the regression of y on xa and xb, okay, b hat a is the one coefficient for xa, this is going to be the same as the beta hat a from regression y tilde on x tilde a. Okay, and here y tilde is the residual from regressing y on xb, and x tilde a is the residual from regressing xa on xb. And this is also going to be equal to, let's say, the coefficient gamma a that you get from regression y on x tilde a. Okay, so these three vectors are going to be the same. Either you regress y on xa and xb and take the coefficients for xa, or you first regress y on xb, xa on xb, and you regress the residuals of the first one on the residuals of the second one, or you regress y, the original y, on the residuals of this regression of xa on xb.